Hi, everyone, and welcome to the USC Viterbi School of Engineering Faculty Roundtable session. This afternoon, our faculty roundtable session is with the Daniel J. Epstein Department of Industrial and Systems Engineering. My name is Paul Ledesma. I'm the Executive Director of Undergraduate Admission here at the USC Viterbi School, but I'm the least important one here. Today is all about meeting with the faculty and learning more about the discipline, the multifaceted discipline of Industrial and Systems Engineering, sometimes referred to as ISE. And so in a second here, I'm going to have you meet all of the faculty, but let me give you a sense of how this event's going to go. First off, we're going to get to know the faculty. They're going to tell you a little bit about themselves, where they come from, what they do here on campus. And then we're going to get into a little bit of detail about the discipline. I'm going to lead that conversation. It's going to be all about the discipline, the major, the curriculum, the classes, the research, everything that happens in ISE. And then towards the latter half of the session, I'm going to be opening up the Q&A feature. And this is where you get to jump in as a live audience. As the live audience, you get to ask questions, and you also get to democratically upvote those questions to whoever the most popular questions are. We'll get through the most popular questions in that order. No need to do anything now. Right now, just sit back, relax, be entertained. I'll let you know when we open the Q&A feature up for everybody. But without further ado, let's get to meet our faculty. We'll start with our professor and chair, Dr. Dessouky.
Hello, this is Maged Dessouky. I'm like if you ask anybody in the profession, I got IC in my genes. My dad was a professor in industrial system engineering. I have a twin brother. He's a professor of industrial system engineering. I've been I've got my undergraduate, my master's, my PhD in industrial system engineering. Oh, I forgot to mention my wife is also in industrial engineering, and actually her career path is very similar to I think what most IACs do after they get their bachelor's degree and move on to the workplace. And I'm sure there's others in my family that are IAC. Oh yeah, my son didn't get an undergraduate degree in IAC, but he got a graduate degree in an IAC related field, and now is a data science manager at the Capital Group. So if you have any questions about the profession, I think I'm reasonably qualified to answer it. I got my undergraduate degree in industrial engineering at Purdue University, and I've always been interested in working in industry, being connected, even in my research. I mean, I feel like it makes me a better professor. So I got my master's while working full time in a simulation consulting firm. Simulation is kind of one of the big tools that we use in industrial engineering. And that was kind of like way back in the 80s where manufacturing was really big in the automotive sector in the Midwest. And I was using simulation all over the place to design factories, run factories, and do all sorts of interesting stuff. But I always knew my dad was a professor, so I always knew I wanted to eventually become a professor. So I went off and did some more work experience at Bell Labs, but I finally made my way out to the West Coast. And once you land on the West Coast, it's kind of hard to ever leave it. I mean, you just don't do it. Very few people do it, and John knows all about this, and Shinyi knows all about this. Um, so I got my PhD at Berkeley, but again, I always wanted to be connected to industry. So I decided to first few years also to work in the corporate manufacturing group at Hewlett Packard, and that way doing planning and scheduling and all sorts of related stuff. After I got my PhD, I landed here at USC, and I just loved it, and I couldn't leave it. And that's just a quick summary of my background. John?
Yes. Hi, my name is John Gunnar Carlsson. I'm an associate professor of industrial and systems engineering. I had a funny path to come onto this field, which is that I was a music major when I started undergrad, and I wanted to do theory and composition. And after about 2 years of that, I said, "Oh, this is not quite the right profession for me," and I wasn't sure what I wanted to do. But I knew I was kind of mathy, and I said, okay, well, I'll do kind of a math thing and see where that takes me, and that was okay. And then I took a course on mathematical modeling. This is like spring semester of my junior year or something. I took a course on applied mathematical modeling. And I thought, okay, I like this. I like this idea of using math to, analyze systems and to describe physical phenomena, right? You would look at like, let's model and try to predict how a disease is going to propagate through a population, or like, let's try and model the flow of a certain kind of fluid in a certain kind of medium. And I thought, okay, this is pretty cool. And then they had a big list of final projects you were allowed to do. And one of them was like, go to a post office and look at how the mail is sorted and determine if you can make a better allocation of the people in terms of like moving them around to improve the, sorting of mail to get more letters through the door faster. And I was like, oh, what do you call that? I said, what do you call this subject of like applying mathematical theory and algorithms and all this stuff to human activities and directing how those resources should be allocated? The instructor said, oh, that's industrial engineering. And I was like, oh, okay, that's what I wanted to do. Like I had never heard of this subject and this discipline, but it was then I said, okay, that's what I'm going to do. So I committed at that point. I said, this is the best thing in the world. It's so rewarding to be using this quantitative kind of methodology to make plans for how resources should be distributed, or how your UPS truck should drive through a city, or where you should build your mobile healthcare sites to provide service to people, whatever it might be. So yep, did the PhD. As Maged said, the California gravity is very strong. I'm from the California Bay Area originally. My first job was in Minneapolis. I spent 5.5 wonderful years there. Although when the chance to come to Los Angeles and be a part of USC came up, I spared no hesitation.
Fantastic.
Shinyi?
Okay. So I have a lot of background, maybe similar to some of you are in this seminar. So first of all, do you know what you wanted to do? I certainly didn't know what I wanted to do. So I get my undergrad, master, and PhD all in industrial system engineering, while I have to take a break between my master's and even in my PhDs, and eventually decide that I'm very interested in industrial system engineering methods, but application, I want to do something of my personal interest in calling. So I decided to do healthcare. So I work as a health policy researcher for many years and decided that I still want to be industrial system engineer. I love the methods, the colleague, the way of thinking. So I came back to USC to become a professor. And then after 6 years, I still feel like my calling is somewhere else. So I joined School of Social Work while still remain my root in industrial system engineering. So now I'm in both schools of Viterbi School of Engineering in the IC department, as well as in social work. And my areas of research is in healthcare services and social services while applying industrial engineering methods. I got my degree close to where John had some of his career. I was in Wisconsin Madison, so Midwest. I grew up in Taiwan, finished my undergrad degree there. So I was an international student and first generation college students, minorities. So if you have questions related to, are you the right fit here? I'm very happy to speak with that. And my answer is yes.
All right, thank you very much. So let me get everybody through a couple different questions, and then we'll get to our latter half where we'll open up the Q&A. So other than describing it as kind of mathy, which I love, I'm going to use that from now on. What is probably the best way to describe what, and I know this is a simple question, probably a complicated answer, but Maged, maybe we'll start with you. What is industrial and systems engineering? And let's talk about that name.
Okay. So I graduated my bachelor's. First of all, if you ask 100 different people, they'll give you 100 different answers. Okay, so that's the first thing.
Yeah.
And people have been trying to fine-tune the definitions since I was an undergrad. When I was a freshman, we used to go to meetings where people would try to come up with the perfect definition of what ISE is. And at this stage of my career, I figured the best way to do it is not come up with the best definition, is do it by example. I think examples are really the best way of doing it. And I'll give you my definition, because I'm sure, and then John and Shinyi can critique it and destroy it, but I'll give you my definition. Applying engineering analysis and techniques to the production of goods and services at the system level. And the key word here is really the system level. And I'll give you an example. In terms of, let's say, if a mechanical engineering was going to work in a factory. Their responsibility was going to probably design the machine. You know, how do we make the machine to efficiently produce a product, or work on any part of the automation of it. The IE is going to be working at the factory, designing the flow of goods through the factory, the scheduling of the factory, the inventory planning of the factory. And, you know, when I started as an industrial engineer, I would say most IEs would be contained into just that factory. But today, because of the globalization, the supply chain is going to be all the way from let's say, can go all the way to China, India, Vietnam, and you'll be designing the entire system from beginning to end to the customer. Now, I would say that the biggest difference between our profession of engineering than any other is the scale of the problem you're solving. The scale. So when we talk about the system, we don't really use the word system but a system could be a small system. But the systems that we look at are extremely large in scale, and they include the human element. So they include the human element that very few of the other engineering fields use. And it also includes financial aspects, which brings you to the linkage to businesses. So all these aspects together come into play into what the industrial engineering do. And I'm going to just pivot on to giving you some really quick examples. I think really this definition I gave is fine, and you could probably understand it, but it's much better to give examples. And I'm going to turn to my colleagues as leaders in the field. One of the things that you may know is if you've been to SoFi, not SoFi, but the one in San Francisco. What's the ballpark there?
Yeah, Levi's Stadium in
Levi's
Santa Clara. Yes.
If you order something while sitting down, the algorithms to determine the delivery and which person delivers it to you are all developed by Professor Carlsson. So this is the kind. I mean, so this is the kind of stuff you talk about, the mathy stuff. Well, this mathy stuff actually comes up with some unique solutions because you can't just randomly assign people to this person that goes to this customer and delivers these. These require complex algorithms, and John was behind it. Professor Wu, she's very much well known for basically, she's probably one of the leading faculty members in the country who's used kind of IE principles to improve the efficiency of healthcare systems. And she was one of the leaders in creating this field. So the last example I'd like to give is queues, because everybody's been in a queue in their life, right? The queues. So our profession has been kind of the leaders in trying to figure out Disneyland, right? So you would think queuing would be important to a place like Disneyland. Well, Disneyland hires a lot of industrial engineers because if you think about it, how you design that queue makes a big difference. Well, when I was, beginning, all queues were basically very much structured very differently than they are today. Before, each server had their own line. But today, if you look at most systems out there, there's only one line and you have multiple servers. It turns out that simple change can save waiting time significantly. And that has changed the way we do kind of the structuring of queues. Another example is if you develop a queue, is it going to be a first come, first serve system or versus priority? Do I have a priority system or versus a first come, first serve system? And you ask, which one should I design? Well, it depends what your objective is. If you care about minimizing the average waiting time, they're both about the same. Both are going to give you the same results. But if you prefer to give preference to certain people or versus others, then you've got to consider a priority. But then again, you're going to give some people less service. You got to consider both the economic and the human impact on such a decision. So I think all these examples kind of give you kind of scale and importance that I would say industrial engineering has done in the workplace. I think you may not know it, but a lot of the stuff that goes on out there is about industrial engineering in your life. One is how queues are done, how things are routed, the home delivery, you all order Amazon or UPS, how they're delivered to your home, all techniques that we do. And because of the broadness and diversity of the profession, that's why a lot of our students go into consulting. initially. About 25% of our students go into consulting initially, and they're very well sought out by the top consulting firms. With that, John, I'll see if you can come up with a different definition.
No, I think yours is fantastic, but I think what I'll do instead is give some more examples, because it is hard to pin it down. So you mentioned queuing, you mentioned lines. I'll start with that one because this is one of my favorite industrial engineering textbooks. It's called "Does This Line Ever Move?" And it's got a bunch of angry, frustrated looking people on the cover. So, usually your textbooks are called Introduction to Microeconomics or, Advanced Real Analysis or something like that. And I love this because this kind of sentiment sort of gets right at the heart of what motivates our profession. It's just, why is this thing inefficient? Why is it disorganized this way? How can I make it better? How can I improve it? How do I analyze this from a systems level? And yeah, there's mathematics that goes into that. There's, computer science that goes into that. Sometimes you'll see elements of physics too, like, well, I need to get this many people across the bridge, but in order to do so, I have to reinforce it here, and so on and so forth. Chemistry can enter that as well. There's certainly a lot of overlap between chemical engineering and industrial if you're trying to figure out the right, mix of chemicals to, to ship to a treatment plant. In fact, actually, I'm right now I'm working on a vehicle routing problem with a large distributor of hydrochloric acid, and they have a challenge that comes up about, oh, this truck can't subsequently contain, this kind of trailer followed by another because this kind of acid causes a reaction with that kind of acid. So you have to let that kind of constraint enter your enter your problem solving strategy. So this is one, if you're the kind of person who waits in a long line and says, I can't stand this, and I'm willing to devote, a significant chunk of my life trying to improve it, like, it's likely the right subject for you. Personally, I took 2 semesters of queuing. Yes,
John,
Maged.
But you forgot one really important topic in this, and that's
Oh, yes.
psychology. Psychology.
Yes. Oh, human factors and psychology. Yes, huge.
Huge.
Absolutely. Okay, yes, absolutely. So psychology enters in all kinds of ways. It can enter in a game theoretic perspective where you say, I think this person wants that, but this other person wants something else. So how do we, create a mechanism to make their behaviors do, what they want, and to align their objectives with what the system wants. There's the human factors angle where you say, okay, how do I design like the layout for this vehicle so that people can understand what's where? And how do I make that kind of configuration? There's behavioral economics, which is, how do I create an economic system that causes a large group of people to behave in a way that is sustainable, that society can function, and not everyone is trying to tear each other down or whatever it might be. What else was I going to add to this? Oh yes, so here's another sort of micro level examples that I think still get at the essence of what the subject is, with sort of tweezers if you wanted to look on the smallest level, and that is well, 2 examples from sort of my childhood, which is that I remember being a young kid, and I was alphabetizing a pile of papers. I had like a stack, I don't remember what it was, index cards or something, and I'm sitting there and I had to sort them. And I had this big, complicated sort of array of cards that were all splayed out there. And my mom sees what I'm doing, and she's like, "Are you alphabetizing those cards?" I said, "Yeah, this is a mess." And she said, whatever you're doing there, that's a very inefficient way of going about it. You're using up a lot of table space, and like, I can tell from the expression on your face that you're kind of struggling with this. And I was like, yeah, this is really hard. She said, no, I'll show you how to sort something. I'll show you the trick for alphabetizing. And she explained the trick, which involves placing, I'll tell you, it's here. Patient sort is the name of turns out that's the name of the algorithm. I've got the background on here. I was going to bring my camera down and show you my hands and walk through it, but it would be kind of time consuming and it doesn't look so good. If you're interested in learning how to alphabetize something really fast, the patient sort algorithm is very, very good. And so I learned that. I thought, oh, that's a great life hack. Now I know how to do this. And it turns out that's one of many algorithms you would learn as an industrial and systems engineer for how to sort something without taking up too much space on the table. Let's say you have a constraint of how much stuff can be laid out, and like you you have limited memory, like you don't want to keep everything in your head too much. So there's a whole, I teach a course on what's called discrete mathematics that has all kinds of variations of that kind of thing. The last one, and then I'll hand this off to Shinyi, is there's, yeah, actually psychology, imagine that's right. I hear some on government, voting theory, right? Ken Arrow and all that good stuff. So there's a number of industrial engineering types who would look at sort of the theory of voting, right? Like, which is just the practice of how do I take a big group of people who have various preferences and form some kind of aggregate consensus out of that, right? You hear in the U.S. in a presidential election or something, it's just whoever gets the most vote is the winner. But of course, there's all kinds of variations of that, and there's a whole subject, a whole subject of like, all right, which systems work well and what are their strengths and their disadvantages. And a fellow named Steve Brams from NYU was giving a seminar talk, and he said, I've been doing studies of mathematical democracy for 30, 40 years, however long it had been. And he said, I always just use approval voting. He said, for every committee I'm on, anytime I need to make a decision, I always just use approval voting. And I said, tell me about approval voting. What is that? And he says, it's simple. Like, you have a group of people and they have a bunch of options. Just tell them to give a thumbs up to every option they approve of. And maybe it's more than one, maybe it's none of them. And then add up whoever gets the most votes. I said, that's so simple. He said, yes, I've got papers and papers proving about how efficient this is. And so that's been my life hack. Every committee I chair, I always, when I have to make a consensus, I say, okay, we're going to institute approval voting because it's backed by this kind of guarantee that it can't be too horrible. So those are three that come to mind. Study queues, sorting papers efficiently, and how to vote well. It's all about, as Maged said, the study of large industrial systems study of large industrial processes at the systems level, where you're looking at how to organize something really big in scale. And now I'm going to stop sharing because I forgot. Shinyi, you want to take it away?
Yeah, your childhood reminds me of my childhood. I remember the first class, I look at the information of my mom's class and ask her, Mom, do you know how many students you have start with the last name of C and D and E? And do you know how many birthday months is in January, February, and March? I'm saying, why would I need to know that? I just love to see the patterns and get things into some sort of system. Yeah. So for me, industrial system engineering, I like the metaphor I learned in my undergrad industrial system engineering department, which is there's always a better way. And we try to find a better way to get things done. So this can involve design, manage, or analyze. So where I see opportunities of applying in healthcare or social services, I see how do we design the system better? So some of my research will get into how do we design better way to coordinate or design better way to support decision making, so decision aid for the providers, for the patients, and design ways where information can arrive just in time, or to identify ways where you can use information to facilitate people to work together. So using the design principles we learn in industrial system engineering, we can improve how the system works as a whole, or how the process can have a better throughput, reduce inventory, reduce waste, and so forth. We also try, including psychology or economics, accounting, and other methods, we try to how to better manage the things we design or people design, how to better manage that processes. So we provide human factors engineering to support trainings, to support the psychology of people working together and understand the system knowledge, so we can improve the system. We also do a lot of data analysis. So now I think one of our biggest programs is the data analytics, where we handle data. So now we have tons of data everywhere, ubiquitous. How do we use the information, the data, to analyze in a pattern, so we can better sorting things, so we can better manage things, we can better supporting the decisions and reducing the queues. So the goals can be many different type of goals, but we have methods to help better design, better analyze, and better manage the systems.
That was great. I think what I would want to summarize, because some of the words I picked up, efficiency, optimization, there's always a better way. And this leads towards, to be quite honest with you, engineering better businesses. And so when we have a lot of students out there that are thinking about combining engineering and business and what is that magical combination, I think you just heard it. This is that perfect bridge between engineering and business. And that's where we get to those ideas of making better ways. So I love that. Majed, would you mind discussing a little bit more, maybe some broad strokes of what the curriculum is like and what
Sure,
types of classes students will go through in the
sure,
undergraduate program to
sure,
get to that point of doing these really cool things?
sure. So your first IC course will be with Professor Wu, actually. So we have that's our first. And you're basically, as a freshman, we'll have an intro course with ISE. I would say the first years, particularly, is going to be the standard for most engineers. You do your GE, you do your chemistry, you do your physics. But starting your sophomore year, you start splitting off. And I would say the curriculums, the mathematical part comes from the probability, statistics, the optimization, um, and those are really the core mathematical techniques. And then you start getting into some, as I said, there's the management business aspect. So you start splitting. So you start in your those are your kind of foundational sophomore level course. And then of course I would add also information, programming, and I would say, I would say information systems. That's another, I would say, kind of foundational. Those are like your base courses. Then I would say then you start then going into more the specialization. So you start doing some of the management courses, or organizational courses, accounting courses. So that's the business courses. Then you'll do, I would say, then applied courses. Supply chain is one of the biggest, I would say, impact areas that our students go into. And so we have a dedicated course on supply chain design, and that uses, I would say, the techniques that you pick up at the sophomore year level. Then I would say the third, I would say, more advanced courses are taking those base techniques and going deeper. So you go deeper in the base techniques, and then you do some applied courses and you do some management courses. And then that pretty much, I think, describes our curriculum in a nutshell. So it's a mix of math, management, and human elements, courses like psychology.
And would you also say that someone that might have interest in data science or data engineering, data analytics, this is also
Absolutely.
the way to go as well, because you can
Right.
somewhat, I don't want to use the word specialized, but you can start to curate some of
Right.
your technical electives in these directions.
Right. Actually, that's actually one of the things that I would say we were probably the first IE department that started embedding the data science AI techniques in our courses. When we went from 3 to 4 units, we started adding those techniques. A lot of the AI techniques and particularly machine learning techniques, are based out of the algorithms that we have developed, like optimization. So a lot of although we may not call it that, but now we basically revamped our curriculum, or I would say you will see topics in these areas throughout our curriculum, in our statistics courses, in our optimization course. And furthermore, as I said, we have now developed more advanced courses in these areas. So for someone who, let's say, has taken the optimization course, who's taken the statistics course and wants to learn more about it, they can take a more advanced senior level course in that area further down their curriculum. So I would say we were probably one of the first departments who basically revamped the curriculum to include these new data science and AI techniques. And in fact, we offer a master's course program in analytics, which is very popular. And if the students take it as part of the BDP, I'm sure that's something that you'll talk to the students about if
Yeah.
we're interested in down the field.
Great. For anyone who'd like to jump in here, can we talk about what happens after the undergraduate years? Of course, I'm not talking from like a data perspective, but more from an anecdotal perspective. Where do you see students go on to? We know that a grand majority go straight into industry. Some students go on into grad schools. What are the types of companies? What are the types of jobs? Where do you see them? What do you see them doing these days?
Majed, you probably are best equipped to answer that, but
Yeah.
I'll say a few words before doing
Go ahead.
so. A lot of
Please
them
do.
go to big consulting firms, Accenture and so forth. That's a lot of it. A lot of them have some kind of passion that they cultivate during their time of study here and decide to devote themselves to that. We have one student who I can think of two. One went to Southwest, one went to Boeing, who they both were really coincidentally they just loved airlines and they loved air traffic management and trying to manage resources of that kind of stuff. This is what I want to do. I'm going to move that route. One student, she ended up realizing how supply chains could be really helpful for like an Etsy shop that she was starting up. So she did a startup. We were just in touch a few months back. She was asking about, oh, can you recommend a good integer programming solver for taking care of this kind of thing. That was pretty cool. Yeah, they go. Some of them go to Disney. That's a big one. I don't have the raw numbers offhand, but yeah, oftentimes there's some kind of cause that they're particularly interested in, and then they go and pursue that. But I'll let the others chime in with more real information than just anecdotes.
I'll say that the students, if we graduate 80 students, we will probably find 75 companies that they all work differently. So I think that's what the beauty about industrial system engineering is that students can go to a lot of different career opportunities, whether they are more mathy or more management or more business. These are all opportunities for the students. So in the areas that I know, some students, they will go to like Apple, Microsoft, those big companies, as well as some healthcare systems or Tesla car companies. It's just very, very broad. I think the most common actually, yes, I see the most, if we put into one category, which is consulting, otherwise it's really very broad companies. I took students to visit the UPS recently, and one student, I would never thought that she would be interested in UPS type of services, and she was so fascinated with this company. She said, "I want to do an internship there. I'm probably consider my career there." So this just speaks to the breadth of the possibility for our students.
So I think that the unique characteristics that our students have is they have the ability to understand broad, undefined problems and attack it through some kind of analytical technique and to give a solution that can be implemented. And yes, that's why consulting companies like our students, and in fact, they're usually the first stop that these companies do. And if you name them, they've been hired by students. Name any consulting company that's well known, I can point a student who's worked there. But but that's only 25%. So that other 75% is all over the place. I'll just tell you the story of one student who was an undergraduate student, and he was very much interested in working in entertainment, but he wanted the training. So why did he study our field? Because he wanted that broad, and it's where you understand the business aspect, the operations aspect, and kind of the analytical aspect. And so he went after, and he wasn't the first, but the Universal had NBC Universal. They had the program, which was kind of a rotating position where you'd hire you and you rotate, and it was kind of a way. And he worked for them for several years, but eventually he made his way to Amazon Studios, and now is helping to run Amazon Studios here in Culver City. So that just kind of gives you an example of the kind of the broadness. It doesn't mean that everybody does this, but you have an opportunity to learn a very desirable skill set that you could probably apply it to almost any industry. I know graduates are studying who are now working as in the UN relief organizations. So I mean, it's everywhere. So these are the extreme cases, but the most common are going to be working in some kind of logistics or transportation or service industry like Disney, and they're numerous. But the key thing is that you want to work in ill-defined problems that can have a big impact. And you have to have the ability to think in the abstract and put it all together and use some kind of, you can't come and make a recommendation. Yes, this is better because I think so, right? Yes, we always can do better, but telling people this is the way to do it because I think it's better is not a selling point, especially when you're young and trying to make a sales pitch. So you've got to make a systematic engineering argument to it. And that's what we train people to do. And I'll just leave it at that.
In some ways, the ISCs are the Swiss Army knife of the engineering pool.
Exactly.
They can be used for a number of different purposes across any different field, and you always need one. Every single firm is hiring, every single company is hiring ISCs. So that's a big thing.
Yeah, and I want to say that because the field I work with, I also see many students working in healthcare and even social services.
Yes.
In LA County, the chief of staff of the Justice and Care Opportunities Department is our PhD graduate, and also
And undergraduate.
and undergrad, master.
And yes, yes.
Right. And also in state of Washington, their director of data science is also our graduate.
All right. Very cool. This would be my last question. So kind of a fair warning to our audience, I am opening up the Q&A function. So please feel free to jump in, start typing up your questions. Please try to keep your questions to one single question per entry. You can keep asking a number of different questions. Just don't load up multiple questions into one entry. Ask as many questions as you like. And if you then see questions that you do like, you want to see answered, upvote them to the top, whether you've asked questions or not. This will be a democratic process. We're going to go through the most popular questions up at the top first. And we'll do that right after this last question. So get in there, hit that Q&A button at the bottom of your Zoom screen. There's a little Q&A button. You can start typing in your questions and get as many going as you possibly can, because that's going to dictate the last half of our session. So my last question is about the future. And, while we all don't have necessarily crystal balls, but the idea of what are you all most excited about in the field, in this multifaceted discipline of industrial systems engineering for maybe the next 5 or 10 years?
I can go last, or I can
Then
go
I'll go first.
Yeah.
Sure.
I think the thing that's going to differentiate it today from today is the scale of the problem. The scale of the problem keeps getting bigger and bigger because as the world gets more connected, it's going to get more connected. There's just no doubt about it. That means the scale of the problem is going to be much more, much larger. And so what does that mean? So we're going to be able to solve them because I think of 2 reasons. Because as the scale gets bigger, it gets more difficult to solve the problem. I think what's going to happen is, of course, the speed of computation. When you get into quantum and all these other techniques, parallel computation, the computational field is going to improve significantly. But what just as important, I think we're in the age of algorithms. Algorithms are getting much more sophisticated, can do things that we couldn't dream to do. So they go hand in hand. You have the computational, I think, efficiency that the computer scientists and the electrical engineers working on that are going to do it. But I also think that that's not going to solve the problem. I think the algorithms are going to have to get more sophisticated to be able to solve the scale problems that we have. And that's it. I'll tell you the biggest difference between today when I was a student, the data wasn't there, right? So I don't care how good of an algorithm I could develop. If I didn't have the data, it didn't matter. It's kind of like garbage in, garbage out thing. So we were building these huge data. My generation was building these huge data warehouses because that's you need as kind of a bedrock before you can use that. That's there now. Those data warehouses are there and they're going to keep developing. But now that they're there, we can start using them to develop algorithms to make really great decisions at the scale that's going to be needed for the future.
John?
Yes, I was looking at one of the questions here, and I'm not gonna jump in on, but it actually my answer is very much related to that, which is the amount of data that we have and the scale, coupled with the rapid innovations that are happening in artificial intelligence, coupled with the slow I don't want to say encroachment, that's a negative word, but the way that technology has started to influence the physical world in the sense that you have more self-driving cars and drones and these new kinds of logistical systems that no one would have thought of, 10 years ago, your Ubers and your DoorDashes and all these different kinds of modalities of getting things to people. The advancements that have been made technologically, in terms of, oh, my hardware can do this now and it couldn't do this before, means that you have this giant fountain of sort of new interesting problems to look at. There's one that I particularly like, which is UPS has a van that has a drone on top, and the drone can pick up packages off the van and drop it off somewhere. It's been a prototype for a long time. And that's really cool technology. No one really knows how you actually use it efficiently. Like, when should you launch the drone? When should you not? Who gets what? And that kind of like sort of hardware level innovation then leads to similar kinds of innovations that are needed for our field. So whether it's self-driving cars or drones in logistics or high-speed rail, like there's all kinds of interesting questions that come out that we get to sort of sink our teeth in. So we're always sitting here like, eagerly awaiting the latest technology innovations to see how we can, improve it and contribute to it.
So for me, I think the technology advancement is really exciting, and I'm more interested because my area of interest is in how do we lift up the humanity ground. So I'm particularly interested in what kind of research I can do to bridge engineering methods, technology advancement, and human needs and community needs. So that's what I feel really, really exciting. And also I feel, yes, there's a lot of challenge and people are scared of how this technology advancement is going to lead us to. Are we going to get better life, better pay, better manage, better time, better life? And so that's the type of research I'm particularly interested in. I think hoping to bridge more the engineering side with the human needs, so we can have impact that's making a better quality of life for all.
Thank you so much. Once again, folks, get in there and ask your questions. The one thing I forgot to mention, and there was one question that I have dismissed out of there, is that please no questions related to admission or the application process, because we have a number of other events where we run full admission processes to provide much more detail about that. This is our opportunity to talk with the faculty about the curriculum and everything related to the discipline. And so I'm going to put a little note in the chat here where you can sign up for another event to learn more about the admission process, and also from our website to learn about the application process. But let's focus on the faculty and the disciplines today. Again, ask questions, keep asking questions, keep upvoting. Don't forget to upvote, because that's the order in which we're going to be going through those. So right away, the first question that won the most upvotes, Idara Ekpo, you win the prize. You get the most popular question for today. The question is, and for anyone who'd like to answer, does ISE collaborate with other engineering disciplines? And if so, how?
Okay. I could do
Go
this.
for
ahead,
it.
Maged.
Yeah, go for
I
it.
think I could do this. So yes, because yes, although we're broad, we have to know the details, right? So we work with, so let's say we work with mechanical engineers, right? The mechanical engineers may design the particular machines. We have to know those capabilities so we can understand how it could be integrated at the systems level. Okay, so if we do it in the chemical engineers, we consistently collaborate with, we have centers collaborating with both computer scientists and research centers collaborate with both computer scientists and electrical engineers, because in the computing platforms, they may be focusing, so double E's, they may focus on the computing aspect of it, but we're focusing on the algorithms. So we have to know what the computing capabilities are. And sometimes you develop specialized algorithms making use of the computing capabilities. So that's with the double E's. And in the computer scientists, as I say, the fields of machine learning and optimization, they're merging, right?
Mm-hmm.
So I would say we focus a lot more, I would say, on the decision-making process. So at the end of the day, the goal is the decision, right? The goal is not the tool. The goal is the decision. And I see the question about AI coming along, and I'll kind of, when we get there, I'll talk a little bit about why I see AI less of an impact in our profession in terms of a negative impact, in terms of a replacement. I mean, I don't see AI being something that we ignore as professionals. I don't
Just
see.
go for it now. Let's just go for that one now, and then talk a
Let's
little
go
bit more
for it.
about how ISE is
Okay.
really at the core of a lot of AI anyway.
Yeah,
Yeah.
okay. So that whole point is is AI going to replace me? I mean, that's the question everybody asks, right? Well, it's if you look at programming, it's much easier. Like when they talk about replacing them, they talk about replacing beginning programmers. They don't really talk about replacing more experienced programmers, right? That's going to require very sophisticated, and we're maybe years or never get there. So let's talk about why that's less so for terms of what IE is. Because we don't work on something that's kind of like reproducible, right? So everything is almost so unique. All systems have this unique aspect. You have both the business angle, you got the engineering angle, you got the human angle, you got the operations angle. That's very difficult to replicate. And we're always trying to come up with a decision. Each decision has its own goal, objective, and unique characteristics. So reproducing that is very difficult. So what I see our profession is using a lot of the AI tools to help us make better decisions. I don't see the AI tools replacing our capability to make decisions. But I think we're years and decades have been thinking about that.
And if it does, we'll adapt.
Yeah.
We're very resilient as a field.
Yeah, and to the point of like, I like how you went down to the AI question because that was Devin's question, if I remember correctly. Devin, you asked that question. I'd go ahead and put that as answered because this idea of working with other disciplines, if you can't tell so far, ISE is involved in everything. And, to create that amazing space technology at SpaceX, yeah, of course, aerospace, mechanical, electrical, astronautical engineers, ISEs are involved at every step of the level, and they're coordinating, they're creating the synthesis between these ideas and understanding a little bit more of the optimization, a little bit more of the math of some of the stuff and how they connect those details. So really it's the that not necessarily a 30,000-foot view, maybe a 10-foot view of really hands distance away or arms length away of dealing with the details of the issues. And you can equate that to every single complex product down the road, whether it's from, cell phones to complex things like Levi's Stadium, which I can't wait to go back to, and then claim I know the person who's responsible for this.
Get a hot dog, yeah. Get a hot dog. Check your watch, Paul.
You get the hot dog and call it the Carlsson dog, right? That's what we do.
And you can time it, and if it's off, you can text me and say,
Yeah, now we're
who's
now we're
accountable.
talking. All right, let's keep going. Our next question is from Ariella. It's for Professor Wu. How are you incorporating community service with industrial engineering?
One of the things we do in industrial engineering is to reduce waste. And I wouldn't say in community services we have a lot of waste, but I'm sure there's a better way to get things done. Who do we serve? How do we serve them? What information is needed to serve them? How do we arrange the services? Right now, nonprofit organizations or community service organizers, they don't really use the tools. We know how to better arrange the services, serving the people more efficiently. And so I think that's one way we really can bring a lot of help or collaboration in that aspect. So that's where I see in healthcare, in social services, really by collaboration, by teamwork, we really could do a lot better.
Great. Thank you so much. Our next question, and again, we got a little under 10 minutes left, so get in there, ask questions, get in there to upvote if you see a question you want answered over others. We've got just about 9 minutes left to be able to get through the rest of these. So from Alexander, you're welcome. And his question is, I'm curious how ISE students at USC work with industry leaders, projects, internships, etc., and how important is mentorship or how mentorship might work at the school or within the department. And one thing I forgot to mention is sometimes I know we talk about outcomes. We talk about all these companies that students work for. They work at those companies because they had the internships before that. Like they're interning with all those companies. And I forget that sometimes students miss that connection. So when we talk about companies students are working for, that's the same companies that are recruiting for internships down the road. So let me just get that out, and whoever wants to jump in here. John, were you going to jump in?
Sure, why not? So number one, we have this capstone project at the end of your 4 years, which is where you're in a small team of 3 or 4 three or four of your peers, and then you work directly with an industry collaborator who's, you know, had some kind of longstanding engagement with our department. So we have this whole Rolodex of, you know, companies that have like hired from our department that are sort of well entrenched in the Viterbi and industrial and systems engineering ecosystem. So that would be the most direct way. In addition, I'll just say, I mean, I'm on LinkedIn all the time. And you know, when the courses that I teach are often at the, say, sophomore or junior level, and when I see an internship that comes up that looks like a promising opportunity, I just, you know, shoot it to the Slack channel or whatever it might be and say, hey, you know, here's something to consider if you're interested in this. And then there's always job fairs at USC. If you notice this, every time you walk through campus, there's always these tents up there with people who are eager to talk to you and learn about what you're interested in and what makes you tick and if you can contribute. So there are a lot of opportunities there. It was about mentoring as well. Certainly that kind of collaboration fosters a ton of mentorship. We are a very social department too, in the sense that we have an active IISC. Sorry, we have a very interactive, a very active student chapter of the Industrial Engineering Society, and there's a lot of good mentorship opportunities there to talk with people who are senior to you or guest lectures from faculty, this kind of thing.
Absolutely. Great. I think I'll add, I don't think you'd see this type of faculty doing this at other schools and universities. The fact that they want to connect, they want to talk to you now before you're even applying, that lends itself to this world that they're here to help you. I don't know if you recognize this. And as you can tell, they're nice people, right? They like to do this. They like to work with you. And they really get joy out of giving you that mentorship and the next steps to your success.
I would say one of the things we excel at is the industry connection, because we have a department advisory board. You can look at our website and see who's members of that. We're very prominent people. We have a student organization which has constant industry speakers who are local, because we tend to be local. So and our graduates, you'd be surprised, a lot of them, if you're not from LA and you come and study here, a lot of our students say, I want to stay in LA. So we have a lot of graduates still working in and living in LA. So we do, and John gives you perfect examples of senior design. We're the only Viterbi department that actually senior design project is a project from industry. It's actually a project that you work with industry solving a real problem. So when you go out there and interviewing, you could talk about that. Most of them get a chance to talk about through their internships. Let's say you didn't do an internship, you were doing summer school or you were studying abroad during the summer, so you didn't have a chance to do an internship. But you'll still have that senior design project experience. So when you go on your interviews, you could say, yes, here's the project that I worked on with a company or even a nonprofit, using IE techniques to solve an important problem. So you'll get that connection.
Great. Moving on, our next question is back with Ariella. So first time, second question asker here. What are the most important skills students develop in industrial engineering?
I'll jump in. I think the most valuable skill that that you learn that the specific field would be the skill to mathematically model things. This is what I think they really excel at, which is that when someone describes a problem they're facing in the real world, and you say, oh, I know how to translate the issue you're facing into something that can be, you know, solved with computer code or solved mathematically or whatever it is. It's that language of saying, okay, I get the problem that you know, the manager are facing. And I know that perhaps there's parts of it that you know, you don't fully understand. There's parts you're having difficulty putting into words. The ISC is all about taking that verbal description and turning it into something that's actionable and real. And that's I think that's something that the ISC majors do that no one can even come close to. It's like central to what we do.
John, you beat me.
I know.
I know you beat me because I think
that's why I jumped
actually,
in.
I know, because that's actually when people ask me that question, what differentiates the best IEs? And I would just say those who can think in the abstract. Right? Because you are, at the end of the day, you will be building some kind of model. And you cannot replicate 100% of what goes on in the real world in that model. You cannot, because you just cannot solve that if you include every single detail that goes on. But you want the model to be reflective enough of what's going on in the real world, so that means something. So the question is, what level of abstraction do you put in the model to get meaningful results? And it's always a trade-off. And you're taught by this, by building a lot of models of different types, and the best are the ability to develop the level of abstraction they need to include in the model.
Yeah, I'll add to, I think one of the skill is very important that we learn in ISC is the multi-level system perspective. So we see problems not just from a tunnel vision, but it's more a system view where the different level from the organization to process to individual workers or the system outside the systems of system perspective is quite unique for our major.
So Paul, it's not one of the questions I do want to get a chance to
Go for it.
I can answer for very quickly. There was a question about how do you get involved in research. So the school, Viterbi, has some kind of research programs for to support undergraduate research. But what's unique about our department is we also have that same program within the department. We have some very generous donors who believe in undergraduate being involved in research. And so we have some funds to support undergraduate research projects. The only thing that's required to do it is you have a faculty member who says, okay, I'm willing to do this with you. And you'll be surprised. There's a lot of faculty who raise their hands and do it. So that's another one of the things I think that differentiates us from most of the other, not at say Viterbi programs, but most of the other IE programs in the country.
Could I share one paper that came from an undergrad research that really quick, 30 seconds?
You bet.
This was a student in the marching band who said, I played the trombone and my arm moves around too much when I slide the trombone back and forth. And he said, can I optimize and move my arm as little as possible? And he did this. He's at Rand Corporation now. Yes, he came up with 4 different methods and proved which one was best. It was great. And I was a musician too. I played the trombone also somewhat.
Go back up to the title. Go back up to the
Yeah,
title again. What was
optimizing. Yes.
A network-based shortest paths approach to musical expression.
Yes, this was great.
Did it make him a better player?
It gave him a good story to tell.
I was gonna say.
Actually, but
you know,
on the subject of modeling, if I may, on the subject of modeling, though, it was important because he came to appreciate that it wasn't just about not moving your arm so much, but it was about expression and saying, oh, well, this one is more efficient, but it doesn't sound so good because of the way you have to, do what's called the embouchure and all that. So he came to appreciate this notion of what's called the Pareto frontier, which is when there's multiple objectives that you're trying to optimize and you have to trade them off. So he's even got Pareto curves in this paper, but anyway, I want to make sure I don't go over.
There's a nice parallel here too. Sometimes efficiency is not necessarily the best path, and ethics gets involved.
Fair enough. I will concede that. Yes.
Well said.
Because I was going to say, like, was he better? Well, he finished the halftime show 30% faster than anyone else in the band. All right, y'all. On that note, thank you for all joining us today, and big thanks to our faculty here, Dr. Dessouky, Dr. Wu, and Dr. Carlsson. We appreciate you representing the department. If you have any other things you want to learn about our programs, come to one of our other events. We have in-person and virtual events. I put a link in there, viterbi.link/events. Other than that, thank you all for coming. Have a fantastic evening and fight on.